Well, how did you do? Hopefully it's obvious that the cross-sectional area in the thick wire is greater than the cross-sectional area in the thin wire. If that's not obvious to you, then you haven't understood what cross-sectional area means. Now, the other thing is that N, which is the conduction electron density, is a property of the material, and so it's fixed. It can't change. And charge conservation simply dictates that all of the charge that enters one piece of wire must exit the other, or equivalently, all the electrons that enter one piece of wire must exit the other. So the two electron currents must be the same. So that eliminates B and A and E. And so we're left just to think about where the speed is greater, in the thick wire or the thin wire, and this is now just like the highway and the cars. The speed must be greater in the thin wire so that the currents can be the same in both, despite the difference in the cross-sectional areas. Note that in the case of a road, we end up getting traffic jams because the drivers can't or won't speed up as they enter the narrower piece of road. But traffic jams, or in other words charge buildup, simply does not happen in wires. And so we know that the currents are the same in both parts, and that means that the electrons must be moving faster in the narrow piece of wire. Well, I've already talked about charge current by analogy with money current in the parable of the debtors and creditors, but here's another analogy. If we continue our traffic analogy, we could talk about the coffee current. If these are early morning commuters, then there's some volume of coffee per car in every car, and so the coffee current would just be the amount of coffee per car times the cars per hour. So similarly for electrons in a metal, the magnitude of the current is just the electron current times the magnitude of the charge on the electrons, where notice this is a magnitude. We don't care about the negative sign, it's just telling us that the charge current is in the opposite direction to the electron current. More generally, if we have anything else, like a solution with ions in it, then the current will be the charge of the charge carriers times the charge carrier current. And since we have an expression for the electron current, we can then get this full expression for the current in terms of other things, which rearranges to look like this. Well, it's been a long road, but we can at last write down Ohm's law. So we know that for a wire of some uniform cross-section A, we can write its current in the expression that we developed. And if that cross-section A is the same everywhere, and we know the current has to be the same everywhere, that tells us that the E field strength has to be the same everywhere inside the wire. We have a uniform E field. And so now if we talk about a wire of some length L, and there's some known potential difference across the wire, then we know that the E field strength is related to the potential difference over the length. And so we can just replace that in our expression for the current. And this, at last, is Ohm's law. So we've arrived at last at Ohm's law, which relates the current through a resistive circuit element, say a resistor or a wire, to the voltage applied across that resistive circuit element. But you may be a little confused at the moment because you may have already met Ohm's law in an earlier course, and it probably looked a lot simpler than this. Well, don't worry, we're about to simplify it. Let's pull it apart. So, it has a part which depends on geometric properties of the circuit element. In other words, the shape and size of the circuit element. It also has another part which depends on the material properties. In other words, what the circuit element is made out of. Let me just focus on those material properties for a moment before simplifying it. So, it contains E and M sub E, which are the fundamental charge and the mass of the electron. So that's assuming that this circuit element is made out of metal or something else where the charge carriers are electrons. If our circuit element is, say, a container full of a solution, then we would have to replace those with the charge on the ions and the mass of the ions. Then N is the charge carrier density, and tau is the time between collisions. In any case, all of this is determined by what the circuit element is made out of. What's usually tabulated is just the end result of all that, which is called the conductivity. So everything in the purple box there is usually just replaced by a single number called the conductivity, and we're going to use kappa to represent it, which is the Greek letter that says k. Now let's just verify that Ohm's law does what we think it should do. So if we take a given battery, and we're going to keep the same battery, so the voltage is being held fixed, and we replace a thick wire with a thinner wire, then we expect that the thinner wire ought to carry less current. And indeed, Ohm's law shows us that, because the current is proportional to the cross-sectional area of the wire, so a thinner wire will carry less current. Also, if we replace a short wire with a longer wire, we again expect and observe that the current should decrease. And again, Ohm's law shows that, because it shows that the current is inversely proportional to the length of the circuit element. Finally, if we just replace the wire with a wire made out of a different material, we again expect that with the same voltage we would get a different current depending on the relative conductivities of the two wires. So we can write it all this way, replacing the material properties with the single quantity kappa, but usually the way we write it is to say kappa AL are all to do with our conductor or resistor, and so we replace it with 1 over R, where R is the resistance. Note that that's defined that way so that when the resistance is large, that means for a given potential difference, we will get a small current. And it usually gets rearranged this way. And just note that what we are talking about here is the potential difference across a resistive circuit element, a wire or resistor, and the current that goes through that same resistive circuit element.